and welcome to the last session of the workshop. Our first speaker is Mats Carlsen, who will talk us everything about chromospheric heating.
Thank you. So I will start by going through some results from numerical simulations, and it's the one that you all know by now. That is the published one that we call enhanced network. So what can we learn about chromospheric heating from such an experiment? Well, when we look at the temperature range in the simulation, that is in the temperature range 7 to 10,000 Kelvin, this is a vapor visualization software written here in car. So here is a plane at height equals 0, tau 500 equals 1, and you see that some of the matter above tau equals 1 is in this temperature range in the granulation, overshooting granulation. There is some magnetic field marked here in red and blue. That's hard to see. And here you have sort of chromospheric material. And as a function of time, you can see these big oscillations, and they are from the starting, or there are some inconsistencies that set off excite global oscillations. This also saw, just play it once more. Also see the oscillations in height in the photosphere. So that is something, if you analyze these simulations, you have to take into account. But we see that the matter is, at least at the upper end here, or 8,000, is concentrated where we have the magnetic field. The nice thing, of course, with this simulation is that you can go in and look at all the details. And that is pretty important, because we often say that we need a given number of kilowatts per square meter, or some units, to heat a chromosphere. And that number comes from not observations directly, because in the chromosphere the lines are optically thick. So even an absorption line can be cooling the atmosphere. So to add up the cooling, you have to really go into a model. So those numbers are model dependent. And what we get in this model, the energy balance, is that we have here the total heating in watts per cubic meter, and in the log. And this is the total, and we see that up to some height of about 1 megameter, it's dominated by the viscous term. So there you have shocks responsible for much of the energy input to the chromosphere. Above, it's in this model, it's the dissipation of the magnetic energy that's transported up through slow braiding through ohmic dissipation. So it's a Joule heating. It's maybe hard to see this yellow curve here. And there is some also absorptional radiation from the corona, and it's quite a lot less than these other terms, but it plays a role for the temperature structure in the upper chromosphere. The cooling terms are the detailed radiation here that is treated with some scattering recipe, and then we have these non-LTE recipes implemented in Bifrost from calcium and hydrogen, the light blue curve there. And this is the optical fin. So of course in the corona, the optical fin losses take over. But you can also see that the cooling here is smaller than the heating. So at this time step, it's still not in sort of quasi-equilibrium, it's slowly heating up. And the numbers here are in the same ballpark as in the semi-empirical models, but slightly lower. So the simulations, are they really realistic? Well, we often call them realistic, and that is because of the ambition that we want to include all the physics and then sort of have an ab initio with as few free parameters as possible. And the main free parameter is the magnetic field configuration that we put into the box. So that is the meaning of realistic when we call them that. But when we compare them with observations, which is then the goal, that compare with observations and learn from the differences, we see here that the K2 peak separation, that was one of the measures that Jori talked about yesterday, does not fit. So here we have the histogram of the observations peaking at about 30 kilometers per second peak separation, and we have about half of that in the simulation. So our profiles, that's also shown yesterday by Jorit, they're in from the simulation, they're too narrow. And that, of course, you all saw as well when you played around with the synthetic observables yesterday. The profiles are narrower. But they do go into the regime of the observations. So we believe that we do have many of the physical parameters as in the sun, but we don't have the right mix. So we have too little of the hotter, denser, and early temperature rise that you have in the sun. But we believe that we do have some of them, so the relations we talked about yesterday are robust. It's just that the sun is in sort of the one end of the range where we have these relations. And it also goes for the peak intensity. This is then the K peak intensity in radiation temperature, and we do have sort of these bright pixels that go similar to what we have in the observations. But there are discrepancies, and we interpret them as that we have too little chromospheric material, we have too little heating in the chromosphere. So why? Well, one possibility is in numerical resolution. This is now just a small box, 6 by 6 megameters, so we can then run that in the photosphere and see the effects of the driving, and this is the spatial gridding of 48 kilometers grid dimension horizontally that we have in that simulation. And when we go to higher and higher, up to 3 kilometers in this last one, we see a lot more structure in the granulation. And that also leads to a lot more structure in the velocity field. This is the vertical velocity at z equals 0. And we see a lot more structure. And that's also evident if we look at an intensity image. This is from this 3 kilometer resolution simulation, so it's 2048 by 2048 grid points. And this is done goes only up to 700 kilometers, so we don't have the chromosphere corona. So the idea is first you relax it, so this has run for many hours of solar time, and then you extend and put on the chromosphere and corona. And then you wait 4 years, and then you have some results. But you do see a lot of vorticity, you do see a lot of small-scale details, and we do excite a lot more motions in the photosphere at this resolution than we do in the one that we have analyzed. So we believe that that is one of the ways of getting things closer to reality. So we have narrower profiles, too little emission on average. We don't have enough chromospheric heating. So we want to increase the resolution to get more dynamics, more exciting waves and other motions in the atmosphere. Also, the magnetic field has only a large-scale structure because of the way it's introduced in the box. By specifying it the lower boundary at 2.5 megameters depth, then we can't really get things on a horizontal scale of much less than 2.5 megameters, and vertical scale of much less than that either. So we now also introduce horizontal field, and of course at a higher resolution we also have local dynamo action, so we get more of these small-scale fields into the chromosphere, and they can do work there. But it's also possible that ion-neutral effects play a big role here in the chromosphere. So from the simulations, we still they should be viewed upon as numerical experiments that we can learn from, but they're not certainly quite away from being an accurate description of solar conditions. So then let's go to observations. And I will show 2 examples, and this is collaborative work, this first one with Jaime de la Cruz and other collaborators, published there. And this is about heating close to magnetic flux concentrations. So these are observations from Palma, from the Swedish Solar Telescope. And you can see in the wing of the calcium 8542, you see clearly where you have magnetic field. Even better, we have magnetograms. And the profiles you see are marked in the figures, and the circles, filled circles, are the ones that you see underneath. And the green ones are then in sort of quiet regions. And so this is typical quiet sun, the 3 examples. The blue ones in magnetic flux concentrations with increased wing intensity, that's why it's bright here. But it's also increased in the core. And then you have these positions that are sort of slightly outside the magnetic field concentrations, where you have filled in cores in the 8542. And that is a sign that you have at the height where the core is formed, it's hotter. It's sort of the same, similar temperatures as in the flux concentrations. And then we can look at, see if we get the same in the simulation. And yes, we do. Here we have a wing intensity. It's slightly further out in the wing than in observations. Here is the magnetic field, and this is the core intensities. And what we see is that here is a quiet sun profile. Here is one of these raised core profiles that's close to magnetic field concentration. And this is the one from the magnetic field concentration. And then we can apply the knowledge from the tutorial and look at source functions. And see, here is the source function for the flux concentration. And it's deep down. Here it's cooler than outside. But you see this is tau equals 1. You see deeper, so it's bright. Even though in the photosphere it's actually at the given geometrical height, it's cooler. And that's a well-known effect. Then the core tau equals 1 are marked here. And for the brown, here we go, this is the temperature. So the source function decouples from the temperature and then falls. So you get a pure absorption profile, even though you have a temperature rise for this blue profile. For this orange, you have a local maximum, so you get a double peak. And this is where the core is formed at about the same place as in the flux concentration. So you get about the same intensity. And for the quiet sun, it just falls off. And here is a cut. And we see that we have the flux concentration. So here it's hotter outside, but a bit up, it's hotter in the flux concentration. And this is where we have this point. This is a cut along there. So this is the flux concentration. And here is where we're looking. And we see that where the core is formed, we're in this canopy where it's heated. So that's why we have this kind of profile. And then, of course, we should produce the same figure for iris, which is not in that paper. And we have for this filled in this position, these are now source functions for magnesium. They look very much the same. And we have the increased wing intensity in the flux concentration, also increased peaks. Now we're formed really much higher. And you have a much enhanced width at this location. And I'll come back to that. But, of course, we want to look at, do we see this sort of canopy in the simulation? And if we then look at the temperature at sort of this canopy height at 40 or 460 kilometers up, you do see that the flux concentrations are hotter. They're cooler down, but they're hotter. If we scan in height, you also see that here they're cooler. And now they start to get hotter than the surroundings when we get up to these 400 kilometers or so. And there the heating is done by Joule heating. So it's where you have the gradients in the field that you get the heating. So you get it at sort of the edge of the canopy. So that was heating close to magnetic flux concentrations. Now I go to plage, the other case. So this is ongoing work that will be submitted very soon. So this is with Jorrit Lennartz and Bart Dupontier. And Jorrit also showed this figure yesterday. So here there are the big symbols here correspond to the same colored profiles in magnesium K in the lower panel. And here you have another set of examples. And what you see is that the ones that are, and this is sort of in the wing, and then it's closer to the peak, or it's a core wavelength, or was it? This one here? Yeah. But the interesting, we should concentrate on the sort of plage, not in the sunspot. You have a pure emission profile, single peak profile. In the plage profiles, they are higher intensity. You have just almost filled in central reversal. And you have a variety of them, and this is the average for the whole field of view. And they're pretty wide. So you have a raised core and pretty wide profiles. While the subordinate lines are all in absorption for these points. So then you can do some other numerical experiments. You don't have to do numerical experiments in 3D, as long as you sort of extract the information that you can from the experiments. You can also do 1D to see the sensitivity of parameters. That's what we have done here. The red curve is sort of the best fit semi-empirical model that Jorit could construct. The green here is an average profile. The red here has a rather good match. You need some extra macro turbulence in order to get an even better match. But the objective of this modeling is not to get sort of the model, this is what the sun is doing, but rather to look at diagnostics. If we change a parameter, what changes in profile? What does the profile really tell us? And the position in column mass of the transition region has to be pretty low. So this is in kilograms per square meter. So you have to do the conversion if you prefer centimeters or grams per square centimeter yourself. And then you have it varies from light gray to black. And you see that if you go really deep in, you get higher peaks. You need to have it at a rather high column mass. Otherwise, you get a big central depression. So in order to get this raised core, you have to have the transition region at a high column mass. If you change the temperature of this plateau, here it's 6,500 degrees, you change, these are the changes in the width. You don't have a lot of changes in the profile. You get some, well, you do have some changes in the peak profile. We said that they're measured typically of the mid-chromosphere, but here these peaks are actually formed in these very steep temperature rise, so they're not so sensitive to the temperature here. There you would, to probe this, you would need other diagnostics that we'll come back to. You need to have a microturbulence. You see here, if you change the turbulence from 2 kilometers per second to 9 kilometers per second, that affects the width of the profile. And this is where the temperature rise is, but then the microturbulence is set to very low values, so the profile is, but it's only to show that the wings, the damping wings, depend a lot. If you put this at a very high column mass, then you get the damping wings to dominate the width of the profile. So the extra diagnostic that we have is here, the subordinate lines. So if you change the temperature here, then you can quickly, if you make it too high, you quickly get them in emission, which we don't observe. And the same if you have the temperature, the low temperature rise, if you have it for really low, as Thiago showed, you also get the in emission. So, observations. This is a one dense raster, 400-step raster. And it's special in that it has a spatial summing of 2 pixels. I'll come back to why we did that. But there is no summing in the wavelength domain, so it has the full spectral resolution. And this is plage. If we look in the wavelength of the peak here, and then scan different positions, we see these profiles that are filled in, central depression. If we come out of the plage, then we have lower intensity in the wings, and we get this self-reversal. But also note that it's pretty homogeneous here. The profiles are pretty similar. If we look at the width of the line, it's also very smooth in this plage area, and it's filling in where you had between the flux concentrations in the photosphere, so this is much smoother. And what will be clear later today, when Lynn is giving her talk, is that what we mentioned yesterday is its oxygen 1356 line, and this is the reason why we had this binning spatially on board, so we can get a signal to noise that's good enough, at least in the plage, to determine the width of this line, which is a optically thin line that can be used to constrain the microturbulence. And in the quiet sun regions, then you have a lot of noise because of not enough signal. So if we look at, have some mask, this is a very crude mask, so it only includes sort of the bright parts in the photosphere. But to do some statistics, these are the widths. So here we have all points, ranging from 15 to 40 kilometers per second. And the plage points has a much, much narrower distribution. So you have wider profiles than in sort of the average, or wider profiles than in the quiet sun, and there is a rather narrow range. So it's a good diagnostic. It has to be that the part that's sampled by these peaks has a rather homogeneous sort of space-filling magnetic field. These are the widths of the oxygen 1356 line, and these are in sort of microturbulence units. So it's clear that the turbulence is on the order of here 8 kilometers per second. I haven't subtracted the instrument width, so it's a bit smaller than that, maybe 7 kilometers per second. And so that is the turbulence that you're allowed. It's an upper limit to the turbulence that you have. So there is quite a lot of what we call opacity broadening. And we can look at the correspondence between then these widths in the oxygen line and the widths in the magnesium line. And here you see a cloud of points. These are all points, and there is some correlation. But if we just look at the plage, then it's very concentrated in these widths, as we saw in the histograms. And you don't see much, well, could be some correlation, but it's, there is, of course, some errors here as well. But in summary, for the plage, you have broader oxygen profiles that can constrain the microturbulence, or the turbulence have to have both micro and macro turbulence will be contained in these optically thin widths. And then we can use the width of the magnesium line to constrain the temperature structure, because then we can't sort of play around with the microturbulence or non-thermal velocities as a free parameter, because it's determined here. And then we'll come up with all the secrets of plage chromospheric heating when we're finishing the paper, but that part is still in the works. So what ranges we can have of the chromosphere and what that means also in the heat input. So, conclusions. These realistic numerical simulations, they're not realistic in the sense that they don't reproduce everything that we see in the observations, but they are what we call then realistic with quotation marks, meaning that they are meant to be, that it's possible to compare with observations and really learn something from the differences. It's not that they're so idealistic that you can only sort of not produce observables and compare. So yes, you can produce observables, and we're doing it, and they don't have too much in ways of free parameters, but they do have some ways to go. And IRIS gives very good diagnostics of the chromosphere, and especially combining the line widths of the oxygen optically thin line and the other diagnostics is really promising. But it needs some, also there, some more work. Thank you.
Thank you very much for this clear presentation. Questions, comments? We have lots of time, 6 minutes.
So I'd like to know what actually really is going on in your energy equation. For instance, if I poke a hole in the photosphere I can access radiation temperatures of 8,000 Kelvin, which is higher than most of the chromosphere. Therefore, from first principles, you can't rule out a lot of radiative heating in the lower chromosphere.
Yeah, but I mean, that is included. We solve the radiative transfer equation. We follow the rays, and it's done in full 3D.
Yeah, at what kind of resolution?
At the resolution of the simulation. So here it's a 48 kilometer horizontal grid size, and vertically it's around 15, 20 kilometers.
Okay, so you oversample the H minus scale height by about a factor of 2 or 3. Okay.
Yeah.
So you mentioned a lot of stuff, like there's a lot of joule heating in the upper photosphere. Do you really believe that's true, or is this a manifestation of a sort of low magnetic Reynolds number calculation? I mean, you've got effectively a very viscous fluid down there, and you're dumping a lot of energy in, and it's coming out. I mean, is it really not true that, I mean, to what extent is the mechanical heating greater than the radiative heating as a function of height through the atmosphere? That's sort of the question I'd like to know the answer to.
Well, the mechanical heating has, I mean, you can't do it all with radiative heating. I mean, you can to some extent, but you get...
Emission lines, but yeah.
Yeah, I mean, you wouldn't get a temperature rise. You get some, you can get some even in a radiative equilibrium model,
Right, exactly.
but it's not much. It's way too little compared with what you see.
And you trust your calculations to tell you that accurately?
Well, I trust that people have done, it has been done sort of a careful radiative equilibrium calculations where you get this Carrel effect and you do get a higher temperature than the sort of, if you don't take everything into account, but it doesn't produce any of the, I say here that we were far off, but if you compare, if you calculate the synthetic observables from those models, they're way away. I mean, they don't have any emission at all in the magnesium lines. So, yeah, I'm confident that you need to have mechanical or magnetic or some extra non-radiative energy input in order to explain the observables that are created in the chromosphere. But yes, the joule heating that we get, I mean, it's the way these simulations can dissipate the magnetic energy that's built up, and that in the real sun will happen at very different scales than we have, and it can be in different forms of the energy release. But it has to get rid of the energy that's sort of transported through the magnetic field also in the sun.
And do you at all worry about the fact that there exists this entire class of solutions that your code can't forget, namely the weak tangential discontinuity class of solutions?
Well, I mean, we do what we can do, but it's also true that it's sort of a robust system that you do build up the energies, and you build up these the currents or current sheets, or you have to dissipate energy, and it can be done in very many different ways in the sun than we have in the simulations, yes, but you have an energy buildup, and it has to be dissipated. Otherwise, you just build up the energy all the time.
I think we go on to comment on this and then Tom.
I have a comment on this business with weak solutions, because MHD can handle weak solutions. I mean, for example, a shock is a weak solution, or a gradient in the field. I mean, I really don't understand that comment.
Tom?
Yeah.
Never mind.
Tom?
You mentioned fairly early in your talk when you were describing the energy balance in the chromosphere. On the radiant cooling side, you described the effect of many weak lines. So you have what you call absorption lines, but of course we know that any line is in emission. It's just the core of an absorption line is less emission than the wings. And so your point is that there's a forest of moderately strong lines, iron lines, for example, as Anderson Appé calculated years ago, that possibly could contribute significantly to the rate of cooling of the chromosphere, in addition to the resonance lines that we all recognize are very prominent cooling source. So my question is, how do you actually treat that effect numerically, of this forest of this haze of lines?
Oh,
And how important is it too?
it is important, and it could be done better. What we do here is opacity sampling through cruise line lists, and then we have them in scattering, so we have just a 2-level scattering recipe with an epsilon that's calculated from Pan-Bregemotter. So, and then the scattering is dealt with as worked out by Scutlien in the 2000 paper. So there is scattering, and we do have all this forest of millions lines, but the non-LT treatment is not as good as in the earlier work.
Other questions?
In your talk, and also in previous speakers talk, mentioned non-LT recipes.
Yes.
It is published or is available?
Yes, those recipes are published in a paper by myself and Jorrit Lennartz in 2012.
Okay, so let's end our symposium. And we move on to the next talk with Steve Bradshaw, who will talk about pinning down some of the heating properties in the presence of non-equilibrium.
All right. 10 minutes? Oh no, I was counting on an hour. All right, so if I was a particularly terrible person, I would speak extra loudly this morning, but I shan't on this occasion. So yeah, okay, so I want to talk a little bit about some work that Paula and I are planning to get involved in on looking at how one might start pinning down coronal heating properties using iris observations, but trying to take some account of the tricky issue of non-equilibrium ionization, which has been mentioned on a handful of occasions so far this week. So the reason that we sort of wanted to get into this work is that, as we all know, nanoflare type models of coronal heating predict that at the onset of the radiative cooling regime, in the corona, we see temperatures sort of in the range of, or peak temperatures at least, somewhere in the range of 3 to 5 million degrees. But in order to get those kind of temperatures at the onset of radiative cooling, you need to heat your loops up to somewhat significantly higher temperatures, right? So they go through some sort of thermal conductive cooling regime before they hit the radiative regime. So one of the things we're after to try and really pin down whether these things are actually taking place in the corona is to look for evidence of high temperature emission, particularly from sort of 8 to 10 million degree type plasma. And we have assorted X-ray instrumentation that's both been flown and is coming online. I'm thinking things like New Star and Eunice and Foxy and the forthcoming Magix as well, which will hopefully help us to identify this stuff if it's there. But as has already been mentioned, it's tricky to observe high temperature emission because the plasma that gets heated to high temperatures isn't very dense, so there aren't many photons. It cools very quickly because thermal conduction is pretty efficient at high temperatures, although there's some caveats here because actually in these kind of temperature and density regimes, the Spitzer-Hahn type conduction that we all put into our models breaks down catastrophically badly. And so if you want to really actually get a handle on how energy transport's taking place at these high temperatures, then you need to do significantly more sophisticated calculations that take into account very strong flux limiting and even non-local thermal conduction. And then, of course, there's our old pal non-equilibrium ionization, which just means that if you're heating a not very dense plasma up to high temperatures very quickly, then creating the ionization states that are characteristic of high temperature emission before it cools down again might potentially be difficult. So at the moment, until the X-ray instrumentation has something a bit more definitive to say, we wondered if we could look for nanoflare signatures in transition region emission, particularly observed by iris, because as has already been said this week, it's very dense down there, there's lots of photons, and the transition region is very strongly coupled to the corona, especially through sound waves. So some sort of pressure increase in the corona, maybe due to heating, there should be a very fast response in the transition region. So the first couple of questions we wanted to ask ourselves is the straightforward one: what actually are the signatures of non-equilibrium ionization down there? Are we actually sure that we're dealing with this problem in the first place? And then once you've got that, how can you do something useful with the observations? If this is really taking place, then how can you actually extract something useful about the properties of heating, given that what you're looking at could potentially be quite misleading because it's out of thermal equilibrium and everything. So this is the kind of iris data that we're interested in, and this was kindly prepared for me by Paula. So in this case, this is the sort of region that we're interested in looking at, and a nice bright sort of loop footpoint region, and the iris slit jaw field of view is green, and the slit is the red bit. So we keep that in the same place, and we're looking for variations in the footpoint. This is the iris 1400 angstrom silicon 4 slit jaw image, and you can just about see that we've identified 3 positions along the slit, A, B, and C, which are sort of just about visible there. And then we take that and we plot light curves. This is in the silicon, and the oxygen line, which correspond to the positions A, B, and C along the slit, right? So A at the top, B, and C, and the silicon emissions solid and the oxygen emissions kind of dotted. And what we're seeing, and as has already been pointed out, in fact Paula herself said it, is that we see a lot of variability on very short timescales. I mean, certainly less than a minute, and there's even been evidence for variability down to about sort of 15 seconds or so. So our working hypothesis is that this is the transition region responding to things happening in the corona on those kind of timescales. So we want to try and predict what the actual signatures of non-equilibrium ionization might be. So to do this, we perform just a very simple numerical experiment where we heat the corona, and then we look at how emission formed in the transition region that falls within the ice sensitivity range actually responds. So in the left-hand column, we just had a 15-second nanoflare going off in the corona. In the right-hand column, a 60-second nanoflare. And what we see, and we calculate this emission taking account of non-equilibrium ionization, right? So we solve the ionization balance equations in a time-dependent manner to predict the intensity integrated along the line of sight as a function of time. And what we see for the 15-second nanoflare is the oxygen 4 emission, this is the non-equilibrium emission here, is enhanced sort of a little bit, maybe a factor of 2-ish, thereabouts, over the equilibrium calculation. But the silicon 4 emission, I've actually had to plot on a log scale because the non-equilibrium enhancement of the silicon 4 emission is actually quite substantial. And in the 60-second nanoflare calculation, it's even greater. I mean, the oxygen 4 emission, is increased by sort of maybe an order of magnitude-ish, but the silicon 4 emission has jumped up, as you can see, by something like several orders of magnitude. Okay, so this effect could be rather significant. Now, the reason for the increase in the emission is just that is what I've called here sort of a non-equilibrium temperature broadening. And what's happened is that the increase in pressure in the corona and local flows has shoved the transition region much further down the loop towards the surface. And so these ions have been carried into much higher density plasma. And of course, the emission in the optically thin approximation scales is the density squared. And so we're seeing much brighter emission just because these ions can survive for a bit of time down to much deeper layers. Okay. And actually, as Phil mentioned the other day, another possibility there might be the density dependence of dielectronic recombination. The dielectronic recombination essentially gets killed that low down, and so that might help these ions persist into even longer as well. So these effects might even be underestimated somewhat. And actually we've also found, I'm not showing it here, that non-equilibrium effects are actually more pronounced at higher densities because, again, higher coronal pressures shove that transition region even further down the loop. All right, I'm going to move on a little bit. So we want to look for signatures of ionisation, we want to look for emission lines with different ionisation timescales. So by way of an example, if we look at, say, the ionisation rate of silicon-4, which is about 3 times greater than that of oxygen-4 and silicon-4, where they form, we see, again, for the 15-second simulation on the left and the 60-second simulation on the right, that the predicted ratios in equilibrium, which are these dashed lines, are very different to the predicted ratios in non-equilibrium. So if we see sort of ratios in this kind of range somewhere, then we might be able to be sort of reasonably confident that we're actually looking at non-equilibrium ionisation signatures. And there are sort of interesting implications here for things like density diagnostics in the transition region, which we've already talked about. There's an oxygen-4 line pair that it seems might be fairly sensitive to this. So this is the sort of Chianti predicted line ratio as a function of density. And we find, again, for the 15-second nanoflare, actually, it's not too bad. The equilibrium and non-equilibrium ratios are kind of similar. But for the longer period nanoflare, the non-equilibrium calculation predicts a higher ratio. And if you figure out what that is, then we find that the non-equilibrium calculation predicts a density of about sort of 0.6 dex higher than the equilibrium calculation. And if we actually go into the simulation and look at what the density is at the equilibrium formation temperature of the line, we see it's lower than might be predicted observationally. So really what these density diagnostics are is it's just telling you the density in the plasma at the temperature sort of where most of the emission is coming from, okay, not the temperature at which this line is formed in equilibrium. So before I run out, I just want to say something quickly about diagnosing coronal heating from this. So we've sort of plotted a bunch of sort of line intensities as a function of time for some different iris lines. And what we see is there isn't really a clear timescale in their predicted variability that actually recovers the heating timescale. In this case, it's about 60 seconds. But, I mean, we see, for instance, things like the iron 12 variability is kind of similar in both of the simulations. But of course, in the non-equilibrium simulation, the intensities are a bit enhanced. But the one sort of line in here in the non-equilibrium simulation that does sort of somewhat more closely follow the heating timescale is this oxygen-4 line. So when our diagnostics are telling us that strong non-equilibrium ionisation might be present, then this sort of serves as a guide to the actual sort of line that maybe we should be looking at the variability in to sort of at least land somewhere in the heating range. In the range of the heating properties. But I'm going to skip this stuff because I'm running out of time. So I'm just going to put up this sort of summary and conclusion, and just sort of say that that the line intensities we expect to show different characteristic patterns of evolution when you take account of non-equilibrium ionisation. And somewhat weirdly, these effects are more pronounced at longer heating timescales, because essentially the ion population has more time to depart from equilibrium, and somewhat oddly at higher densities as well, but that's because the pressure increase is higher, so it can shove the transition region much further down the loop. And there are one or two little other things that you can read for yourselves, so thanks very much.
Thank you very much, Steve. Chris, Don.
Yeah, Steve, any thoughts on unique criteria or a test to show evidence that it's non-equilibrium versus, I mean, you mentioned suggestions of ratios of different ions with different time scales, but
Yeah.
Clearly this non-equilibrium ionization is what there probably is going on. The question is how how can we use that analytically when we're looking at
Analytic, okay. Well,
it? And probably a whole other talk, of course.
yeah. Well, I mean, if we're looking for signatures of it, this is my sort of our best idea at the moment is to look at these ratios for ions that have very different formation timescales. As to how you might deal with it analytically, that's a tough question. I've not reached any satisfactory conclusions yet. Our best approach, I think, is this combination of observations and modelling, and I think in the next talks, I expect we're going to hear quite a lot more about that and how one might go about doing it. So yeah, I think the thing to do is to try and match as many observables as you possibly can within the parameter space of your simulations, and yeah, that really is my best guess at the moment.
Your model says something about the heating going above in terms of conduction, and then the radiative is
Right, okay. Okay, yes, so the simulations I've run here, I just dumped energy into the corona because that's sort of what I was interested in. I have nothing against the possibility that heating might be taking place lower down. You know, I would expect the effects to exist. I'm actually not certain, just off the top of my head, how some sort of foot point heating simulation would compare to this. But you know, if you're interested in foot point heating, I don't see any reason not to pursue that as well. And I expect that's one of the things we'll look at in our forthcoming work.
Marcus?
Maybe this is a question for Coronal. Can you speak up a little? Is there observational evidence for 8 to 10 million degree plasma outside flares in Coronal during the regions of fine sun?
Yeah, I think so. I mean, the UNIS guys, is Adrian here? They've seen, yeah, and Jeff as well, actually. I mean, they've seemed to have found pretty strong evidence in is it the iron 19 line in the UNIS?
It's an iron 19 line. We see it throughout an active region. That's an EUV emission. But yeah, we see that line is very faint, but it's over a large area of an active region.
Inoda has seen this too. At least we had press releases about it. We saw it.
Just look
Yeah,
at
very
the
important
picture, you have
press.
the background there on the screen.
Oh, yeah.
It's absolutely black outside active region. So if there's any
Well,
8 to 10 million degree plasma out there?
I mean, I wouldn't go with that. I've done a little bit of image processing on this to sort of fade it into the background so it doesn't get in the way of the overlying text. So I wouldn't take that too seriously. Yeah.
Is the atomic data for these lines so well known that you can tell the difference between the equilibrium line ratios and non-equilibrium line ratios?
The atomic data for iron is pretty good. Actually, it's very good. So there's been a big effort called the Iron Project that's really put a huge amount of effort into calculating these things. So I wouldn't bet my mortgage on it, but you know, I'd say we're sort of within the sort of 10% error range now, which I think is maybe even better actually, which I think is pretty good.
Thank you, Steve.
Cool. All right, cheers. Thanks.
And we continue with non-equilibrium ionization effects. Thomas Bowling from Oslo. Minutes.
Good. Cheers. Thanks.
All right. Yeah, so I'm going to talk about a new module for the equation of state in the Bifrost code, which takes into account non-equilibrium ionization of both hydrogen and helium. So if we first spend some time with the ionization state of these important elements in the atmosphere. So the ionization state of these abundant elements in a typical atmosphere model is that deep down you have dense material. So it's mostly described by LTE, or well described by LTE. And further up, the density drops, and then you get these radiative transitions which become important. And also the timescales for ionization and recombination increase and also go above the typical dynamical timescales, which means that you have a time-dependent situation. So why would we worry about the ionization state of these abundant elements? And that is because of the following. As we learned from Boris the other day, the internal energy is one of the fundamental variables in the Bifrost code. And it has two kind of components. It has the first term, which is the kinetic component, and the second term, which is the ionization component. So for a fixed internal energy, you could have a low ionization fraction, which would mean that the temperature will go up. Or you could have a high ionization fraction, which means that this term will go down, and you would have a lower temperature. So the question then becomes how we determine the population densities. And this can be done by assuming LTE, in which case you have the population densities just by the Saha relations. Or you could do as I want to do, solve the non-equilibrium rate equations. And then you get into troubles with the transition rate coefficient because it has a radiative term, which in general involves the full radiative transfer problem. And this is quite difficult in 3D and all that, so we need to turn to simplifications. And simplifications has been done for the hydrogen. Urit did in 2007. He prescribed the radiative rates for hydrogen and implemented it into an early version of the Bifrost code. So here I give a demonstration of what happens. The left column is a simulation where you have an equation of state in LTE, and the right column is the non-equilibrium hydrogen ionization case. These two lower panels map out the occurrence of various temperatures at different heights, and I would like to draw your attention to this plateau here, which is present in both, because this is the initial snapshot, but see what happens when I switch it on. So when you switch on non-equilibrium hydrogen, this temperature plateau at about 6,000 Kelvin goes away. So this is all very nice, but one problem with this description is that it did not include Lyman transitions at all. And this might not be very accurate for the upper chromosphere. So I've implemented a non-zero Lyman alpha transition. So I essentially solved the one frequency radiative transfer problem. I have an emissivity and an opacity which is proportional to the upper and lower level. And then I can compute the mean intensity and get my radiative transition rates. And I don't stop there. I also am interested in the non-equilibrium helium state. And for that, I think about the physics in the following way. I have a corona and a transition region, which is emitting in EUV. Some of this EUV emission will be lost into space, and some will be pointing downward and absorbed in the chromosphere by helium and hydrogen in the continua. So I can describe this with an opacity in the chromosphere and an emissivity in the corona and transition region. And once again, compute and get the mean intensity, and I have enough information to solve the rate equations. So I set up 4 2D simulation runs to test these methods. The first one I call LTE. Here I have all elements in LTE for the equation of state. Then I have the HIN run, which includes non-equilibrium hydrogen, which is what you have for the Bifrost simulation, which is released. That's the same one. And then I have the Lyman alpha H-ion run, which includes non-equilibrium hydrogen and a non-zero Lyman alpha transition rate. And then I have a helium run, which includes both hydrogen and helium and Lyman alpha transition. So this is what it looks like. This is again an occurrence rate of various temperature at the different heights. So now we were acquainted with this 6,000 Kelvin plateau. But as you see, there are two more plateaus at 10,000 and 20,000. And those are associated with the LTE ionization of helium. So when we switch on helium, which we do in this run, see what happens with the plateaus. They go away. So the LTE run still has all these three plateaus. When we switch on hydrogen, the 6,000 Kelvin plateau goes away. And then everything goes away for the helium run. So that's very nice. So let's, how much time do I have left? Is the... Oh. All right, so we go into more detail in what happens with the temperature as waves propagate through the atmosphere. So here I've singled out one single column for all the 4 runs. And so this is the height and this is time. And these upgoing lines here represent waves propagating through the atmosphere. So in the LTE run, you see that the increase of temperature in the wave front is not very large. It increases when you switch on more of the effects that I've described. So I will just play the movie up until here about. Let's see what happens. Maybe I'm not able to stop it. Okay, at least the shock front temperature, which will show up here. You see the blue line. Doesn't it loop either? So, oops. So here, have a look at the blue line as the shock goes through. Get very high. So the temperature in the helium simulation is much more variable than in the other simulations. And this can be attributed to the ionization fraction of helium. So when you have a wave coming through, compressing the gas, increasing the internal energy, in the LTE case, the energy will go into ionizing the material, and in the time-dependent case, the ion fraction is more or less constant, so all the energy goes into increasing the temperature instead. Is it over? So this has consequences also for how the mass density is distributed in various temperature ranges. So I think I'm just going to show this one. This is, I computed the magnesium spectra from all the 4 simulations. And it's only a 6-minute time span, and I computed the mean of the K line. So there are 2 of the profiles here stick out. It's these 2, which are the Lyman alpha H-ion run and the helium run. And I attribute the higher intensity in these 2 runs to that you have Lyman alpha heating, both heating and cooling in the chromosphere. So, in summary, now we have a non-equilibrium equation of state in Bifrost. And we have, this leads to higher temperature variations, and it alters the mass density at various temperature ranges. And one cool thing is that with this model we get the non-equilibrium populations out, so we can use this, I'm planning to use those as constraints in radiative transfer computations of helium lines in the future.
Questions?
Tom, how do you specify the incident EUV radiation field?
So it's essentially just, so I assume ionization equilibrium, and I compute thin losses from the corona, typically with Chianti. So it's just a table of temperature.
Other question? What?
So, if you go back to your plot comparing the temperature in the shop.
This one?
Yeah, so when you have the helium, the shop temperature is higher, and that's just because you now don't need to ionize the helium.
Yeah.
So if you remove the helium part of the ionization energy, so that there's no helium latent heat, do you also get this increase in the temperature of the shop?
If I remove helium from the composition,
Yeah.
you mean?
This is wrong. It's stupid, but I just.
So I guess because the time scales of the hydrogen ionization would be still long, I guess. So then you would not have the possibility of putting the energy into helium ionization. So yeah, I guess you would get.
And when the line with alpha turned on at like a 1.5 or 2 megaliters and above, the temperature profile actually looks more like the LTE than the pitch ion.
Yeah, here you mean?
No, it's in the temperature the line profile on the right panel.
Here?
Yeah. So the red line, the H ion now is actually the odd one out compared to the other three.
Yeah, but this is so. But this, you can't really compare it directly because this is like 600 seconds into the simulation, and they kind of diverge. This is just me trying to compare something that hasn't diverged too much yet, but it has diverged kind of. So, no.
Is it very expensive in terms of computational resources to include all these elements? I see you did 2D simulations. Can you include them in 3D simulations?
I am, in fact, as we speak, computing a 3D model. In fact, the same as has been presented here. I start from the same snapshot, and then I add all this stuff. So in terms of computation time, when you switch on hydrogen, it's a factor 2 more. And when you switch on the helium, it's a factor 2 more than that as well, typically, something like that. So it's expensive.
Can you go back to your profile, your magnesium profile? So the Lyman alpha inclusion leads to brighter profile, but the width doesn't compute enormously. Is this more of a quiet sun simulation, or is this more and would you expect it to increase more in width or a plage?
Yeah, I don't think I can answer that question in a good way right now. Sorry.
Now, the simulation is certainly more quiet sunlight to these simulations at all.
Yeah, okay.
Okay, Phil.
If I understand it, these profiles in the far wings tell me that the upper photosphere has changed considerably.
Yeah.
Is that correct?
So what happens when you switch on the H ion is that you get also time-dependent molecule formation of hydrogen molecule formation. So you tend to get a cooler, or you're more likely to develop cool bubbles in the model when you switch on all this stuff, which you do not get in the LTE case.
So it's actually dimmer in the wings when you include them with the hydrogen?
Yeah.
Yes. Okay, I got it the other way around.
All right.
Okay, thank you. And we move on along the same theme. The next speaker is Juan Martinez Sikora.
Thank you. Okay, I'm going to talk
Also about time-dependent initiation, but this time for silicon 4 and oxygen 4, similar like Steve, but in completely different regimes. The motivation is that when we try to synthesize these two lines in a statistical equilibrium, and we try to compare what the observations show us, which is shown with greenish lines in the observations, we don't get the same ratios. This is in average. Then what we are missing here is something that I wanted to investigate a bit deeper. For that, first I will go to the observations. These are some targets on the disk that I selected: quiet sun, coronal hole, plage, two different active regions. One quiescent and the other one with some flaring and emergence going on. And if we look at the maps of these observing targets, this is for the quiet sun. These two panels shows intensity maps of silicon 4 and oxygen, and you can see there's silicon 4 shows way much more emission than oxygen 4. On the right we have Doppler shift and line width, and we can see there's quite a strong similarities between the oxygen and silicon. That's probably telling us that we are observing the same features, which is nice if we want to do any kind of comparisons. When we do the ratio, that's shown in this panel. White means there's not enough signal to do the ratio. We can see that the different features shows different ratios. If we go now to, for example, the active regions, this is a sunspot where we have the same rasters, the same distribution of the plots: intensity, Doppler shifts, and line width. Again, we see same features in the width. That's good, and the Doppler shifts. And now the ratio goes to a wider range. I had to expand the color scale for the ratios. We can see that we can recognize some features. For example, in the umbra, we can see really low ratios. And in penumbra, the ratios are way much larger. Then clearly we see things that has different ratios. And in addition to that, in average, we are getting way much larger ratios than in the quiet sun. And another way to plot this is doing these 2D histograms, where I'm plotting the intensity in the vertical axis for the top panels and the ratio in logarithmic scale in the bottom axis. And these are for the different targets: quiet sun, coronal hole, plage, active region, and the flaring one. And all of them shows more or less same correlation. That's meaning that the ratio increases with intensity. It's true that the correlation doesn't look like the same in quiet sun. This is more like some sort of triangle shape. Here we have some kind of oval shape, and this is like an S structure where we can see in the active region. In the flaring one, it expands over a wider range of ratios. It's hard to see any correlation for the Doppler shift. For the line width, well, we might see some small increase within the ratio. And what are these things telling us? Well, now we go to the simulations. This is a simulation, 2D simulations run with Bifrost, which includes the radius transfer through scattering, conduction along the magnetic field lines. And we include in these simulations to solve the oxygen and the silicon with non-thermal ionization. If you remember the first plot that I showed, that was with a statistical equilibrium, where we can see that the ratios doesn't match. When we do it the same for the non-equilibrium ionization, there's a really big improvement. I'm showing here two lines because I was doing the same work as Uluri did in this case, explained with different abundances. And there's a setup where it shows a better match with the observations. Note that this is in a logarithmic scale.
Then there's a great improvement. What about the variations in intensity? This is the same plot, but now for the simulations, where I plot the intensity as a function of the ratio in a statistical equilibrium. And there's nothing like it looks like in the observations. There's some variation, sure, in intensity, but it doesn't look at all. When we include the non-equilibrium initiation, suddenly the correlation way much better with observations. There's something interesting here where we see some correlation in the Doppler shift and also an increase in the line width. This is most likely because we have a magnetic field configuration that is predominantly unipolar, and there's continuously shocks going along the vertical axis, which is probably not going to happen in the sun. Why we get these things? Well, first, let's focus first on the statistical equilibrium. This is the emission measured as a function of temperature for oxygen and silicon. And when we do the ratio between both as a function of temperature, we can see that there's a really nice correlation, and it changes with temperature for the ratio. And this is because the emission here has quite a big drop in silicon, and it doesn't have in oxygen, which basically means that, these two lines are formed at different temperature. Then if we do this exercise of having a temperature stratification where we play around with different densities, and this is shown with this rainbow color, and try to synthesize and see how it looks like in how they look like in the profiles. All of them has been normalized to the oxygen 4, and you can see that we can have a really wide range of ratios between these two lines. This basically is telling us that the different stratification will provide different ratios. What about the non-equilibrium initiation? Well, what happens in emission that we expand over a wider range of temperatures. Now we don't have that big drop anymore in silicon 4. We reach lower temperatures. And when we do the comparison between these two, there's some correlation, but there's also a big variation within the same temperature of these ratios. And that's basically because we have now dynamics going on, which changes these properties. If we go to the simulation and try to figure out where these ratios increases or decreases and why, and this is the temperature on top, vertical velocity on the bottom. I want you to focus on the solid black line and the white solid line in these two plots. So this one corresponds to the statistical equilibrium and non-statistical equilibrium. And you can see that there's no one-to-one matches between these two lines, of course. Now this one follows the dynamics. And the other thing is that for the statistical equilibrium, we can see that the increase in the ratio happens to be located at the boundaries of these speckles that we have almost everywhere in this kind of simulations. And this is basically because the transition region at the lower temperatures gets expanded to a wider range of heights, which will produce more emission in silicon, but not in oxygen. This happens also a little bit in the case for the non-equilibrium initiation. But in addition to that, we get the biggest increases when we see short gradients in velocities near the speckles. That means this is thermal and dynamic properties of these changes. And this is the summary. Oh, just in time. on Google. I'll let you read. Basically, what I'm main thing is that our analysis reveals that almost everywhere in the sun seems to behave in a non-equilibrium statistical behavior. The fact that we have a good match in Doppler shift and line width, we are probably seeing in both lines the same features. And there's the correlation between intensities and the ratios of these two lines that changes depending on the region where we are observing or the features that we are observing. And that's
Thank you, Juan. Questions? Comments? Pietro.
Did you check the effect of kappa distributions on your
No.
ratios?
No, but what with kappa distribution, what they should really double check is the effects of non-equilibriumization when they want to do diagnostics. I also want to point out that using that for the density diagnostic, for example, is probably really dangerous because we don't have, yeah.
Okay. Oh, Scott.
Okay. Just thinking, have you done the same analysis for the total intensity so that you're not getting killed by multiple component things scaling differently in the two ions?
I'm not sure if I am following your
Various
question.
things going on in the wings that are contributing differently. So if you done it for the total intensity versus the peak intensity.
Oh, right. Yeah, I didn't compare if I did total intensities. That's that's how I did. I wouldn't.
Phil.
So there's this long-standing problem of the lithium and sodium-like ions, namely silicon-porous sodium-like versus the rest. And one of the explanations for that is this, as Vigo showed in 1993, I think. But it's a time-dependent ionization. But there is the answer in the old days, in the 70s and before that, was that Lyman continuum absorption was actually taking out. These have anomalously long wavelengths, and most of the resonance lines of something like Alpine-4 are way below in the Lyman continuum. So what I'm suggesting is I'd really like to see you calculate, say, the 787 line of oxygen 4 at the same time as the, 1400 angstrom multiplet in the system multiplet, and have a look at, see if the Lyman continuum plays any role in your calculations in destroying the intensity of lines below the Lyman continuum. That would be really nice to know.
Yeah, okay. That's something we can try to do.
Other questions? This is not the case. Thank you again, and thank you again to all the speakers. Thank you again to all the speakers, and we have now the last poster session and the last e-poster session and coffee.
Settle down. Just the limit of my skills, apparently, is turning the microphone on. I will hand over to our Iris POC. I will let you figure out what that acronym is.
All right. I just wanted to say a few words about the organization here, and I think we can all agree it was great. And I want to take this opportunity to thank the local organizing committee. Maybe you guys can stand up for a sec so everybody can see who you are. We have Alfred, Rebecca, and Paul, and Scott. And Cheryl has actually done an amazing job. And she deserves her own applause.
I can only second that. These guys have carried my ass for the last 4 or 5 months while we've been organizing. Hopefully next time we have a workshop, there'll be 120 people attending. Pretty staggering that there was 100 people here. So let's kick off the final session of the meeting. Here we go. And start bolting that on.
Thank you.
Yeah. I'm not even going to try. How do I?
Xiao Shenlin.
Xiao Shenlin.
Yeah, thanks. No, it's a...
The formation of the auction 1 1355 line and clinical diagnostics. What looks like the deep atmosphere.
So I'm going to report another piece of iris diagnostic for the neutral oxygen and neutral carbon lines here. And they are actually sitting with the same passband as the carbon 30-35 angstrom lines. And you can obviously see they are relatively weak lines. However, we already seen some very interesting and application from Mart's talk. And as we go along, we could really see they can provide some very useful diagnostic in the mid-chromosphere. So in this study, we used the Fauci chromosphere model to carry out the basic formation mechanism study, and we used the bifrost snapshot to study the dynamics on the formation of both lines. And we used the RH to carry out the non-LTE and the PRD radiative transfer. So this is the cartoon of the simplified model atom turn diagram for both lines. On the left, it's the oxygen model atom. As Mats already mentioned yesterday, the hydrogen ionization degree of oxygen was actually set by the charge transfer with hydrogen. Therefore, the continued population will be proportional to the proton density. Therefore, the electron density for the solar plasma. And after that, it was radiative cascading down to the upper level of our transition, which is denoted by the pink arrow here. And this process will introduce another electron density dependency. Therefore, at the end, we will anticipate a square of the electron density dependency in the oxygen emission. For the carbon line, the electron got photon ionized by the radiation field comes from the Lyman alpha emission and followed by the radiative cascading. In this scenario, we will anticipate the intensity from the carbon line will depend on the Lyman alpha radiation and the electron density. And this is what we can learn from the steady model. Now we are going to study some dynamics. And this is the comparison of our simulation and the real observation data in oxygen one line intensity. So at the right is the result from our simulation. So what we are really calculating is a patch from a quiet sun area that doesn't include the bright magnetic network boundaries. So it's a relative quiet region on a quiet sun. Here we show the main result from our simulation, the intensity, the contribution function, and the formation height. The main message in this slide is that in general, the oxygen line forms optically thin, while the carbon line is a typical optically thick formation. And if we use the contribution function to calculate the formation height, we can see this pedal-like structure shows up in the oxygen formation height. And that is a typical signature for the chromospheric shocks. And it also gives a hint that this formation of oxygen line will be very sensitive to the velocity profile in the atmosphere. So if we take a look at the histogram of the formation height for both lines, we do see they pick up at slightly different layers in the mid-chromosphere. So it's 1.2 megameter, 1.5 megameter respect to the photosphere. And in general, the carbon line will form higher than the oxygen line. So these two lines are actually probing slightly different layers in the mid-chromosphere. So now we are going to present some potential diagnostics we learned from our simulation, and we use the contribution function weighted average to collect the information from the plasma quantities that is relevant to our line forming region. And we try to search the correlation with the spectroscopy properties. So first, we would like to report both of these lines are very good velocity diagnostics, as the Doppler shift of these two lines can be correlated very well with the velocity at their line forming region. And remember, because they are probing at slightly different layers, therefore, if we take the difference take a difference of their Doppler shift, we can actually find the velocity difference between these two layers, where we denote as delta V here. And by studying their line ratio, we also can get the information from the distance between these two layers. Therefore, we can derive the quantity of velocity gradient. So we kind of know what's the velocity profile around their line forming region. And as we already anticipate in the basic formation mechanism, we do observe the square of the electron density dependency in the oxygen line emission. And if we take a look at the line ratio, we also see the 1/, electron density correlation. But it's less tight because the introduction of the Lyman alpha radiation. So finally, since we already anticipate that this formation of oxygen line can be very sensitive to the velocity field, therefore, we try to measure its non-thermal line width and compare with the weighted velocity standard deviation in the atmosphere. That means we kind of try to find out the velocity distribution that is relevant to the line formation. And we can actually also compare with this correlation by assuming some known distributions in the atmosphere. For instance, if we have the Gaussian distribution for the velocity field, we can then derive this red curve here. On the other hand, if we have the flat distribution, meaning that the probability of different velocity are identical, then we retain the green line here. And this is actually a very nice comparison, because then we can sort of understand what's going on, what's the velocity distribution in our simulation box. So now I'm gonna show a couple examples, like how can we really use these diagnostics. So first, this is the data of active region with a small flaring event. So of course we can we can create a velocity map by using the Doppler shift for both lines. And if we take the difference between these two maps, we can create the map from the, on the left, the velocity difference. And to compare, we have the oxygen line width on the right. And we can easily see the brighter regions in the oxygen line width, the yellowish part, can actually correlate quite nicely with the blue patches in the velocity difference map, meaning that the larger the velocity difference between these two layers, the wider the oxygen line profile. And this is a very nice confirmation from the observational data, saying that the conclusion we learned from the simulation actually makes sense, and this oxygen line is indeed very sensitive to the velocity in the real atmosphere. And of course, we can also see the intensity map from the oxygen line can provide information for the electron density, because we can see at the center of this map, it has a very strong enhancement, and it is exactly the position and the moment when the flare happened. And this patches is not just brighter, it's also corresponding to very strong redshift. So we can imagine like a bunch of materials moving down in the mid chromosphere. So I think this is a very nice diagnostic to study the flare. You can kind of see what's the response in this lower part of the chromosphere during the solar flare. On the other hand, for the carbon line, we see an even higher enhancement in that, and this is beyond our conclusion. So this is actually contradictory to our previous conclusion of this line ratio. And what we believe is that the formation mechanism get changed completely during the solar flare for the carbon line. Therefore, we will have to carry on more modeling in order to use this line intensity diagnostic. And here, I just quickly show the same data set Matt has shown previously. And we do see the oxygen intensity, the oxygen line picks up very different signals than the magnesium and carbon too. And I think, and then it shows also that the oxygen line also maps a little bit deeper area in the chromosphere. So I think in general, it can be a very good application that if someone sees very interesting event in, for example, magnesium or carbon too, then one can also look at what's going on in the oxygen. Then you kind of mapping different layers and kind of see the different responses, especially for these lines are both very good velocity diagnostics. So I'm gonna just leave my conclusion, and thanks for your attention.
It's a good talk. We're really broadening the range of diagnostics. Are there any questions out there?
What kind of electron density values do you get for the flare kernels from the oxygen line?
I didn't really look at that, but you can check. You can't get it out. Yeah, because, well, if you believe this, the diagnostic we present here holds. But I mean, if in a flare the range is a lot different from the parameter space we explore here, then. But at least from my preliminary study for the flare formation, the oxygen one actually still keep very similar formation mechanism. So I believe it still have the same proportionality to the electron density. So, yeah, but just keep in mind that what we really learn is in this parameter space.
All right, any others? There's more of a comment. I think you could do some masking, right? On those velocity ratios a bit, blow my head. But yeah, it's a pretty tight correlation. So thanks very much again. Our next speaker sets up.
Alrighty. Okay. If I can figure this out. There we go. There we go. Okay.
Steve Cranmer will give us a talk on driving jets and spicules with alpha waves. The pesky problem that won't go away.
That's right.
Interesting. Take it away, Steve.
Oh, thanks. So yeah, so I'd like to talk about these network jets that were pretty much discovered with IRIS. You know, they're coming up out of, this is a movie from Hui Tian's science paper. These little faint jets, if you can see them, seem to be coming up out of the bright network in the upper chromosphere, lower transition region. We can only really see them well when the tips of the jets are in projection against the darker internetwork regions. And there's a belief that as these things rotate off to the limb, these are really the same things as the type 2 spicules. I think that's still controversial, and there's debate about that, but they seem to have a lot of the same properties, and they seem to behave in the same way. So yes, thanks to Hui and to a lot of others connected with IRIS in terms of discovering these things and characterizing them. There's still no good automatic algorithm for detecting these faint little strands in this noisy background. So each one of the measurements that has gone in has been a human measurement in terms of measuring lengths and lifetimes and velocities. So a lot of work has gone into it. So in terms of models, a lot of times jets usually evoke, as I said, thoughts of magnetic reconnection. There's the classic cartoon there of a bipole emerging, interacting with the open field of one of the two polarities and producing reconnection in a jet. However, these network patches in coronal holes seem to be the least likely place that you'd expect to see something like this. You really do seem to have very much dominated by one polarity with not much of the opposite polarity there. There's debate about that, depending on how good your magnetic field resolution is. But we thought it would be worthwhile to explore this alternative idea that doesn't require reconnection. It's been around for a while. Joe Halvig wrote his first paper on it in 1982. And I just want to say, warning, theorist oversimplifications ahead, spherical cows and things to come. And in the end, we'll have to verify these ideas with more accurate simulations, of course. But the idea is that Alfvén waves can create these things. And we have to go back and think about the ways that these transverse oscillations of the magnetic field can actually propel material along the field. It's not so obvious when you just look at the basic linear properties of an Alfvén wave. It really is, all the motions really are perpendicular to the field. But it can do a lot of things, right? We know that as Alfvén waves damp out, probably via some sort of turbulence, they can heat the plasma. Plasma heating produces a gas pressure gradient. Of course, Gene Parker told us that once you have a gas pressure gradient, you can start to accelerate material along the field. That's the basic way. But there's some other more sort of exotic options also, right? Alfvén waves can exert this ponderomotive wave pressure. It's really a Lorentz force due to the velocity and the magnetic field perturbations. When you do the whole J cross B and figure out the Lorentz force, and you average it over a period, you actually get a non-zero average for this thing, and it produces a net force along the field. So that's been put into solar wind models in the coronal holes for several decades. But there's also an idea of mode conversion, right? If you have strong amplitudes, nonlinear Alfvén waves, and the background conditions are right, basically if the plasma beta is about 1, you can have a very efficient conversion from the Alfvén mode to other types of waves, either fast or slow, some type of compressive wave that has variations in the density and variations in the velocity along the magnetic field. Those things can produce shocks as they propagate along the field, and those can provide additional sort of pressure support to, for example, the cool material in the chromosphere. And it can probably lift up the chromosphere, levitate it a bit. And these have been looked at for several decades. Wanted to say a little bit more about this whole turbulence idea, right? A lot of the older models, like Kudo and Shibatas and others, that looked at the conversion of Alfvén waves to some sort of levitation in the chromosphere, a lot of them made use of sort of sinusoidal wave trains, very simple monochromatic Alfvén waves. In order to make realistic spicules and things with these models, you really needed large amplitudes, unrealistically large amplitudes in order to make it work. However, in recent years, we've learned a lot more about the Alfvén waves. They really do seem to be a lot more turbulent and intermittent. There's a continuous power spectrum of different frequencies there. We went forward and used Odd van Balenhoen's braid code, which there's a movie there of the swaying field lines driven by very simple motions at the photospheric base, and the turbulence evolves and develops spontaneously as you go up through the chromosphere and the corona. It's a 3D, time-dependent, reduced MHD turbulence simulation. We're doing it for the coronal hole, for the strong field network flux tube in the coronal hole, really trying to match the properties of the network jets. Braid seems to do a lot of the right things. These waves propagate up, they reflect, they damp out as they undergo their turbulent cascade. You get the right levels of coronal heating. And also, observationally, the heating rate at any one point in this model is very sort of bursty and intermittent and almost nanoflare-like. So there's been some recent work trying to even explain nanoflare models from a highly dynamic wave-based model like this. Topic for another talk. I just wanted to show an example of what this braid model produces at some point in the mid-chromosphere. This is the transverse velocity amplitude of alphane waves. It's like I said, it's very intermittent. There's peaks of very strong amplitudes, but there's an average of 4 or 5 kilometers per second. This is not the full time dependence. This is the modulation of the amplitude, right? So if we just had a single sinusoidal alphane wave, that wouldn't be going up and down in a model like this. That would have a constant amplitude. So all these variations are changes in the amplitude with sort of the frequency information taken out. So again, very intermittent, bursty type of a model of waves. So then we have to ask what happens to these waves. So we look at this mode conversion idea, right? We notice that in the mid-chromosphere, the amplitudes become nonlinear. The perpendicular magnetic field fluctuation becomes of the same order of magnitude as the radial magnetic field. The plasma beta becomes 1. So this seems to be just the right situation for a mass conversion of a good fraction of this wave energy to a compressible type wave that could steepen into a shock and possibly lift up the transition region. There's a lot of different mechanisms that have been proposed for doing this, parametric instabilities and shear-driven instabilities. The one that we think is the most straightforward one that might be working in the chromosphere is this sort of second-order effect. It basically happens all the time whenever you have any kind of alphane wave. In the linear limit, it's perfectly incompressible. But if you have large values of this frequency, of this relative amplitude of the magnetic field perturbation, and you square it, usually that's a tiny, tiny number, but if this ratio is of order 1, you can have some conversion to a parallel fluctuation, a longitudinal wave that can provide pressure support. There's a plasma beta dependence in this that we had to sort of go back through the literature, and there's been a sort of a controversy from the 70s to the late 80s as to what this beta dependence really is. Steve Spangler did some very nice kinetic models that we ended up using that sort of fall in between some of the extremes that people have claimed over the years. But it's an understandable thing. So we apply it. So we take this model of the alphane waves. We assume that at some point it's converting some of that energy into the compressive waves using that expression I wrote. And if we really want to understand how the compressive waves can lift up the transition region, they provide this extra non-thermal pressure in the upper chromosphere, and figure out how much it lifts up the transition region to produce this levitated jet type thing. We went back to some simpler models to try to calibrate that relation between the amplitude of the compressive wave and how much it lifts up the chromosphere. So in our 2007 paper, we had these time-steady models where we put in acoustic waves, sound waves essentially at the base, and we varied their properties. As you increase the sound waves, the transition region gets pushed up because the scale height gets bigger throughout the chromosphere. And over on the right, it's basically showing you the radial, the height dependence of the compressive wave amplitude, this delta V parallel versus height. And as you put in stronger and stronger compressive waves, the transition region gets pushed up and up. So we can just take this series of models and look at this monotonic relationship between the compressive wave amplitude at a given height in the chromosphere. This height of 900 kilometers or so was something we chose. We called it Z sub B. And look at the monotonic relationship between that and the height of the transition region. If you're curious why we chose that specific height, that actually seems to be the height where there's a maximum efficiency in the mode conversion. This shows velocity amplitudes versus height. We've got the alphane speed, the alphane wave amplitude, and then once we go through that whole process with Spangler's model and all that of producing the parallel compressive mode amplitude, there's this little peak, this little spike of mode conversion that happens in the mid-chromosphere. So we're sort of taking that as the generation point of the compressive waves. and then looking at how they affect the transition region. So we've got this process where we've got the amplitudes of the Alfvén waves, convert it to compressive waves, then looking at the height of the transition region. Here's the result. Here's the transition region height bobbing up and down as a function of time. And we can sort of take this as a synthetic observation. We can look at, if this is happening in a flux tube, then this is a jet that's expanding up, falling back down, expanding up, falling back down. And we can look at these heights as a function of time and measure velocities. So we can go through and compare with observations of spicules and jets and their lifetimes. The end result here is that we can make a plot of the vertical speeds of these structures versus their time scales, their periodicity. And I just wanted to say a little bit about this plot here of the vertical speeds of something in a hydrostatic atmosphere versus their time scales, because there's a very natural dividing line in that plot that's been worked out a long time ago in the stellar community. Basically, if you have oscillations and shocks propagating up through an atmosphere, the individual gas particles sort of go up and they fall back down, they go up and they fall back down. So there's a natural periodicity. When the next shock comes by, if it falls back down to the same position, then it just keeps bobbing up and down. That critical period is plotted as the line there. If you're to the right, then you're very intermittent. But if you're to the left, then the periodicity of these things is happening quicker than it takes to fall back down. So it's kind of interesting that the observations of type 1 spicules seem to fall along this curve, right? Type 1 spicules, we see stuff coming up and coming back down in a parabolic arc. Type 2 spicules and Huitian's jets are to the left of the curve, and we typically see things going up and not falling back down. Whether this really makes sense in terms of a simple ballistic model like this, I don't know, but it does seem to be consistent. The final result is we can take this model of these turbulent generated transition region heights up and down and extract out velocities and timescales for them, and they fall sort of in a plot like this. I've got two different colors on the plots. I didn't cheat. I didn't just say that the dark black ones are the ones that fall in between the observed timescales and the gray ones fall outside. The gray ones here have lengths, would have observed jet lengths less than about 2 arc seconds. So in most of the cases with the orientation that we see, we wouldn't actually observe those. Those really wouldn't pop their head up above the network patch. Most of the jets have lengths of 5 to 10 arc seconds. Those are the ones up here. And the agreement seems to be pretty good. Again, it's a very tentative thing. Conclusion slide. So we're basically saying that these network jets may be a probe of alpha-ionic turbulence and its mode conversion along these flux tubes. To really prove this, we've got to really go to real 3D compressible MHD simulations and see if this whole sort of proposed chain of events work out. And of course, better observations are needed too. And that's it.
Thanks, Steve. Those initial movies remind me a lot of Trace Data from like 12 to 14 years ago. Did Carol Schreiber write about these jets as well? Back in the day? All right, anyway. Any questions out there?
Could you say something more on the perpendicular magnetic field perturbations and what kind of observational signatures we can look for? For example, if you were to derive magnetic field in the chromospheric heights using calcium infrared triplet, do you think we'll have? Could we see them?
I think the best way of really seeing these is kinematically. You're looking at the swaying motions of these things. I mean, there's, when you even for these relatively large non-thermal delta V perpendiculars, in the chromosphere, the overall swaying angles are still going to be small, 5 to 10 degrees at most. That's why in eclipse images, when people look at these strands coming out of the polar coronal holes, they don't see sinusoids going like this because the natural frequencies and amplitudes and wavelengths are such that the angles are very small, but they are observable and they've been seen with AIA. And then you have to assume that the kinetic and magnetic energies of the Alfvén waves are in a certain equal partition with one another. But yeah, measuring the actual fluctuating magnetic field component, I think will even be beyond the ken of DKIST. I don't know.
I have two questions. Your talk is interesting. The first one is, what do you think how the open unipolar flux tubes form? What kind of mechanism?
How do they form? Well, I wish I had I have a cartoon of that. I mean, it's basically, I think, when there's really only one polarity, in the photosphere, it collects into these little 100-kilometer bright points in between the granules, and those expand up as they go out. And if you're in a network patch, there's more of them. If you're in the internetwork, there's fewer of them. You get this canopy in the network. I mean, it's all just sort of the overall transverse expansion of these more or less vertically pointed magnetic fields. Once you get into the corona, it fills most of the volume, and any kind of sort of kink waves become volume-filling Alfvén waves. But I'm not quite sure if I answered your question.
Do you think this process is a kind of reconnection or not?
I'm saying we can go far without assuming reconnection, but if there are opposite polarities emerging, if there are little bipoles emerging throughout this region, then sure, there's going to be some reconnection. The real world usually has both and not either or. Right? So there's probably some going on as well.
It's time for the last one while Sven sets up.
Can you comment a little bit on what you said in the beginning? You're saying that there was a debate about whether type 2 spicules and microjets are the same.
Has it been concluded? I don't know. I mean,
maybe you missed Luke's talk on Wednesday. I don't know. I guess my question is, there are a lot of observations of spicules at the limb that have provided pretty strong constraints on whatever theoretical model people come up with in terms of Alfvén wave fluxes, Alfvén wave periods, heating rates, speeds, heights reached. And I'm wondering how your model compares to those, because it seemed like you picked the velocities out as your constraint, but there are other constraints too.
No, it would be great to start comparing some of these other ones too. Do we know from the off-limb spicules though where the actual foot points are? Can they be traced all the way to things like network versus internetwork?
No, but these things are.
There's a big line of sight confusion too.
Okay. Thank you, Steve, again. And we'll finish off with Sven Wiedemeyer. Okay, great. Talk to us about Alma and Iris, and he has 30 seconds. No, I'm only kidding.
Okay. Yeah, thanks for giving me the honor of the last talk in this workshop, and for you being still here to listen. Alma and Iris, that sounds like a movie title, but probably signals the long-lasting friendship, I hope. And this talk is more like a commercial, maybe a teaser of things that could be expected, and there is way much more to tell about what Alma and Iris could do together. So Alma stands for Atacama Large Millimeter Sub-Millimeter Array. And this is an interferometric antenna array, which is located very high in the Chilean Andes at 5,000 meters. So if you call this high altitude here in Boulder, this is ultra high altitude. And this is a global partnership, because this is a $1 billion project that's organized together by Europe through ESO, North America for NRAO, and also East Asia, so Japan, National Observatory of Japan, in cooperation with the Republic of Chile. So the wavelength range that Alma is probing is from about 0.3 millimeters to roughly 9 millimeters. And this is divided into later than up to 10 receiver bands. Alma has already observed many non-solar targets, and you probably have seen press releases already in the past months and maybe 2 years. So already some exciting results. But solar observations are still in the commissioning phase for good reason, because the way you would observe the sun, I will show you this in a second, is quite different from how you observe non-solar targets. The last major test campaign was in last December. And regular solar observations will be available in next year's observing cycle, which starts in October 2016. Let me start with a single dish result. So you can use the whole array or sub-arrays, or you can use a single antenna. And here's the result of an observation that was done with a single ALMA antenna, a 12-meter antenna. And this antenna scanned the whole solar disk in a in this pattern that is shown in the top right, where Hugh Hudson and Richard Hills, not Richards, worked on. And that enables you to scan the whole disk in just a few minutes. And you see in the left side the result at 1.3 millimeters, and right for comparison in H-alpha full disk map. And you already see here that you can identify active regions, for example, there. So that's a very exciting first result from that. But of course, when we talk about iris here, then we want to see like high resolution maps, right? There's an impression of the whole array, and the array actually consists of different parts. And just go very quickly through this. So in total, you would have 66 antennas, which are divided in one main array, the 12-meter array with 50 antennas, which you can move around with this transporter that you have seen there, to a maximum distance of 16 kilometers apart. And then you have something that you see in the circle there is the compact array, which is staying in this fixed configuration with 7-meter antennas, which can be spaced closer together, and also 4 very fast-moving total power antennas, which are also very important. So if you think of the maximum distance, the maximum baseline, as we call it, of 16 kilometers for the shortest wavelength here at 0.3 millimeters, that in principle gives you an angular resolution of 4 milli-arcseconds, which is quite amazing. But you have to keep in mind this is only relevant for if you try to resolve point sources. If you talk about the sun, then we have emission from the sun that fills out the whole beam of the antenna. That means the area in the sky that the one antenna is sampling. That means you have to do it a bit differently, and we use then ALMA as an aperture synthesis telescope. What does that mean? So in principle, you take the largest distance of your antennas that you have there, and this defines the effective aperture of like the telescope aperture that you're synthesizing. And the individual antennas then kind of sample different spatial components, Fourier components in this aperture, and through that you can reconstruct the point function of this large telescope, and that you can use then to reconstruct millimeter maps, as if you had maybe a telescope with 1 kilometer diameter. So that means we don't expect 4 milli-arcseconds for maps, but maybe 0.3, 0.4 arcseconds at 1 millimeter. And that scales with wavelength, so you clearly could possibly get down to 0.1 arcsecond for the shortest wavelengths. That's the hope that we have there. So just a brief overview of the capabilities. So you see it might be possible to have achieve very high spatial resolution. The temporal resolution could also be very short, because you don't really have to integrate long. The sun is very bright in the millimeter range. Also, the spectral resolution will be quite high, because each receiver band can have up to like 4,000 or so spectral channels, which you can arrange very flexibly. So a lot of things can be done there. And one very interesting thing is here the millimeter radiation is, due to the long wavelength, very closely coupled to the gas temperature in the radiation forming layer. So in principle, you can use ALMA as a linear thermometer of the solar plasma in the chromosphere. And that it has very large potential. Not enough, it even measures the polarization from which you can reconstruct even magnetic field information. So that means you have the continuum intensity, you have magnetic field measurements. In addition, because of the spectral resolution, one can also try to exploit radio recombination lines. Some of them might even be formed in the corona, molecular lines among all carbon monoxide. And those are diagnostics which have to be developed first. There are a lot of things still not known, but they bear a lot of potential. And so I guess one can really claim that we can expect quite some important results from solar observations with ARMA. So the radiation that, how is that formed at millimeter wavelengths? We have non-thermal contributions from gyrosonance and gyrosynchrotron mechanisms, which are relevant in the presence of strong magnetic fields. That means in flares, this will be very interesting to observe flares, and has been tried already with ARMA. And in the quiet sun, for example, the sampled layer changes with the wavelength that you're observing. And that means ARMA can cycle through up to like 3 warm receiver bands, which are simultaneously available. And so you could, in principle, cycle through different layers in the chromosphere and observe there. This is now a first result from Complementary experiment from December. And there was an active region that was observed. The left here is the antenna configuration, so it's rather compact. And I have to put over this ARMA data, test data here, because this is commissioning data, and they have a very strict data policy. But I trust you to remove this, so you can see something. And this is the first test. It has been done with 49 antennas, so it's a lot of them already. And it has been added like over 40 minutes. You see, it's still an early experiment, but we already see some structure there, and it's very exciting. I see this for the first time. Because if you maybe used to other areas we had before, like the BEMA, you see a map here, and I have on the right-hand side, I have degraded the ARMA map to the roughly the same resolution. You really can appreciate this large leap in resolution that we're making here with ARMA. The simplified beam here is elliptical, very funny in this here. So it's 1.5 to 3 arc seconds, and it's time average. That means in the future, with the full capability, we could probably expect much higher resolution even below sub-arc second then. And this was done simultaneously with IRIS. IRIS is pointing at the same target, same active region. And I have the ARMA observation here as isocontours here. And the only thing I really want to show here is that the same features can be identified there. And so it's really, I think it's very exciting when you think that IRIS and ARMA will probe different properties of the chromospheric plasma, and together can give you much more information than already IRIS is doing. So potentially magnetic field information and even the thermal structure, much more directly. Okay, I'm already out of time, so I'm skipping quite a lot then.
Seconds was quick.
Half seconds, yeah. So what is possible? What should we do first? And so currently, until autumn or so, solar observing modes will be defined. That means what will be available for solar observations in the first cycle next year. That means as a solar community, we have to act now and express what we want, what we would like to see first. That could be based on other simulations and observations. And as a first step, we wrote an overview paper, which I just have here, that's available on the web. It's only submitted, not accepted yet or so. But if you're interested, then I recommend to have a look at this. And also feel free to contact us, because we have a network built up for this, in order to really promote this to the solar community, and also to show the wider ARMA community that observing the sun really is exciting and should be some time set apart for that. I just show you some results from the network activities with simulations to demonstrate the potential that ARMA has. This is based on numerical simulations to show you the gas temperature on the left side and the continuum intensity in the middle. You see it's very closely related. It's a very direct measure. Then the most popular model of this workshop, this Bifrost snapshot, you see in the top ARMA at 1 millimeter and 3 millimeter, and below IRIS magnesium wing and line core, just to demonstrate that you could compare these diagnostics and learn which properties are mapped by which and what you could do in a combination with this. This is some result from Maria Lukicheva and Gregory Fleischmann, also working with the same simulation, before simulation. The first attempt to retrieve the magnetic field, longitudinal magnetic field component from this. This also looks very promising. That has to be developed further, of course. And that is a result from Peter Heinzel and his group, where they tried to simulate, based on an H-alpha map on the left, try to simulate what ALMA would see when observing prominences. And this, I think, is already very exciting if we really get to this point. Let me finish then. So keep in mind the regular observations will start next year, October, and the call for proposals will then probably appear next year. Co-observing with IRIS, I think, is high on the agenda for IRIS. And we won't get so much ALMA time, of course. It's very competitive. But if we get time, then I think it's a big incentive to really try to coordinate this with as many facilities as you can. And there are a lot of people busy right now in different teams, in North American team, European team, trying to define these observing modes and to pushing forward the data processing and all these things that have to be done. So if you're interested in following this, then you can sign up for the network. You follow this passively with newsletters and so on. Or even if you have an active interest in this, we're also starting with some teams digging deeper into the details of this in preparation of the first solar observation campaign. And this is just the concluding slide. Thank you.
Thanks, Sven, for leading this effort. I think ALMA will definitely open a door that we haven't really tapped into in the past. We get time for like 1 or 2 questions. So.
In how many radio frequencies can you image at the same time, or with ALMA?
How many frequencies? Yeah, so if you have 1 receiver band, so in the final stage would be up to 10 receiver bands covering the whole range, right? And 1 receiver band can, as I said, have a few thousand spectral channels. And those channels can be arranged in a rather flexible way. So you can maybe have a small region which you have highly sampled, or you cover the whole band. And then you can cycle through different receiver bands, right? And that up to 3 should be really fast, but if you want to have more, then they have to warm up and so on. I think it's very flexible. So the spectral information will be very, very big. Yes, simultaneously, yeah.
Final question.
Well, what an honor. Could you spend a couple of words on the measurement of magnetic field? Because, you know, that is a big item, chromospheric magnetic fields.
Yeah, so I'm not an expert on this, but maybe so Maria Lukicheva and Gregory Fleischmann have worked on this, and there will be a paper appearing also using the Bifrost snapshot. And I think the basic thing is that the radiation comes out in an ordinary mode and extraordinary mode, and the optical depth where this radiation gets optical thick is slightly different. So you get some local slopes of the temperature, and you measure the polarization. And from that you can estimate the magnetic field, the longitudinal component of the magnetic field. They're pretty sure it's working for active regions. We have to see how if it works for the quiet sun. ALMA has a very high sensitivity, so that might work out well. But that's pretty new territory, so we have to develop this first. That's promising, I think.
And thanks, Sven, and all of our speakers in this session. And just want to thank you all again for attending this week, and wish you all safe travels home, whether you're 5 miles from here or 5,000 miles from here. Thanks.
And if you want to check out the talks, they'll be online sometime next week. Right?
Yeah, we'll try and get all the talks out. We'll send an announcement out about where the talks are. But we'll try to compartmentalize them all. Thanks again. It's really interesting stuff, isn't it?
Yeah. Talk a bit fast.
No. A lot of content, right? Yeah.